Hi, good afternoon. I wanted to do this video for those of you who may be out there who are just getting into doing simulations with Cameo Systems Modeler using Cameo Simulation Toolkit. So this video is really geared toward the basics of simulations. There's a lot of good videos out there that Salius Pamalkas has on his MBSE execution channel that are great for all spectrums, whether that is basics or all the way through a lot of the more advanced types of simulations you can do. But this one is really to cover some of those basics for folks who may be just getting into using Cameo Systems Modeler and trying to do a simulation. So that's what this is for those of you who are just getting into this. So what I'd like to do is start by creating a block definition diagram and explaining a little bit about what simulations are typically based around. Before we do that, however, there is a few setup things you may want to be aware of when you're getting into using Cameo Simulation Toolkit. And if you go to your resource plugin manager, you'll definitely want to have Cameo Simulation Toolkit installed. That is an absolute minimum, and then you'll need a license to use it as well. And if you notice in my list of plugins, I actually do not have Cameo Simulation Toolkit as an option. And that's because it comes with the software package for the Enterprise Architecture Edition. So there are some different bundles of software. Some of those may include Simulation Toolkit, some of them may not. So for those of you who do not have that bundled, you can always come to your resource plugin manager and actually install that. After restarting Cameo, after you've installed your plugin, another really good thing to do is go up to your options. And this is specifically for version 2021X. You go to Project. In version 19, you'd actually go to Environment. But in version 2021X, you can go to Project and then go to Simulation. And if we look at the options that you have here, a few things that will definitely get you and mess up some of your simulations are some of these default settings. So I'd recommend setting initialize empty values to 0 to true, unless you're doing a lot with arrays. Then you may consider having that defaulted to false, but I like having it set to true. Another thing that's good is to check model before execution. This can actually trigger the loading of a simulation profile as well, so that's good to have. There are some default languages, so if you're using things such as Python scripts in your opaque actions, you could come in here and change that default setting. But typically I keep that set to JavaScript Nashorn or JavaScript Rhino. If you notice, JavaScript Nashorn says it will be deprecated in future releases, so you may be better off keeping that set to JavaScript Rhino. So now let's jump into talking about some simulation basics. When it comes to simulation, really context is everything. And when I say that, I mean that anytime you run a simulation, it will have some context, or it should have some context. And what that allows the simulation to do is have access to the value properties of that context. So if we run a simulation and the context is this system block, it will have access to the value properties of that block, such as, let's say this is a system that has a value property of engine RPM. We'll type that as a real number, and that simply means that you can have decimal places. If you wanted to have no decimal places, you could use an integer. And there are multiple ways you can type these. So you can always use the T to type things and then change them there. So different ways to add the type for those. You always want to have a type. You need to have a type in order to actually use these in a simulation. So that's really good to know. So now that this system block is created and it has a value property, this system block has access to that value property if we were to run a simulation within that context. So how can we run a simulation in the context of that system? Well, you can right click on that. You can go to run, and then it says the validation rules are not loaded. Would you like to load them? That is that triggering of that simulation profile. So notice now that we have this started, we have the value property down here that has been instantiated. Something also to be aware of is that this system block has been instantiated as well, and it's been given an object ID. So object IDs are very important, and they're something that are randomly generated, but they're good to be aware of because they will actually identify specific instances of different parts of your system. And it's just good to know if it does not have an object ID that it has not been instantiated. And there are times when you'll need to pay attention to that. So let's say we were to create a reference property instead of a value property, and we will call this max temp or max temperature, something like that. And then we'll type that as a real number. Let's rerun this simulation now. Say there's another execution in progress. Yes, let's rerun that. Notice there's no value for this max temperature, and it's because by default, Cameo does not instantiate reference properties, but we can change that setting if we'd like, or we can simply come down here and add that manually, and then notice it now has an object ID. So that is great, and it's good to be aware of. So you could have known that by seeing that there were no values there, but now there actually is a value and it has an object ID. Other simulation basics that are really good to know is we can create things such as an activity diagram in the context of this system block. And then in that activity diagram, we will have access to these value properties that we could then manipulate with other types of actions, such as opaque actions. We'll create a SysML activity diagram, and then we'll use a simple loop. So good thing to know about modeling loops is you always want to have that merge node that will come back up to you, because you don't want to have multiple input control flows in a loop situation where you'd never have a token traverse one of those. So what I'll do now is use an opaque action. And these are really, really useful for simulations because you can enter in almost any type of software script and have that execute during the simulation at that specific point in time. And then keep in mind, we have access to the value properties of the block executing this activity. And currently that is that system block. So we have access to both that engine RPM value and that max temperature reference property. So let's say we wanted to simply output the engine RPM. We can simply write that into an opaque action. And now in runtime, Cameo will come through and get that value, and then we could output that to somewhere else. So you don't need to rename this output pin, but we can. And then what we could do with that is actually send that to some other opaque action, and maybe we're doing some calculations with that, or maybe we're sending that as a part of a signal. Let's say we wanted to send that as part of a signal, so we could create a signal in our model. It doesn't matter where that signal is created. That's more of a housekeeping item for you to figure out where you'd like your signals created. But we'll call this signal RPM data. And then what we'll do is we'll actually add an attribute to that will carry the data of that RPM. So I'll name this engine RPM, and we'll type that as a real number because that is what it is currently typed as. And what we can do is drag that signal into this, and then we can actually take that value and input it into that signal. And then if we had other parts of our system, we could designate a proxy port out of this system to where that should go. And then another part of the system could receive that data. So after we send that signal, we'll just loop directly back up to this. And now we're ready to actually run a simulation. So when we go to run a simulation, what you can do is either run the simulation. So let's do that. And one thing you'll notice is that we do not have any instantiated value properties. And that's because I did not run this with context. So notice it also says that the reference engine RPM is not defined, and it's because it's looking for a value property that it can't find because we did not use the context of that block. So we will run this with context. And as of right now, that is 0. We could change the runtime value down here to something else. And notice we now see that as runtime value. So that's running on a loop. So let's go ahead and add in a time event. We can drag that onto this control flow. And it asks you, do you want to put that before or after the control flow? So one thing that's good to know about that when you're dragging things onto a control flow is that really it's asking you whether or not that should be before or after the guard. So if you had a guard and a decision, then it's asking you, would you like this before that guard or after that guard? So for now, since we don't have a guard, we can actually just say before it. It really doesn't matter. So notice this says at. Well, we could put in that 2s, but at is an absolute time. So if you wanted to make that relative, we can go to our properties, scroll down to the bottom. Notice we're highlighting the time event. And then there's an option to change that to relative, and then it changes that to after 2 seconds. So now if we were to rerun this with context, what you'll notice is it'll get to that time event and just wait there 2 seconds and then continue. So that's a nice way to use time events. Now, let's say we wanted to send that signal to another part of our system. Well, we need to have parts of our system in order to do that. So this gets into another very important concept, and that's dealing with parts of a system. So let's say that this is our engine, and then let's say this is our computer. And these are currently 2 parts of our system. So what we now have is one part property of this system that's called engine, that's typed or defined by this engine block. And we have another part property or another part of our system that is called computer, that's defined by or typed by this computer block. So if we were to simply run the simulation now, what you will notice is a few things have happened here. We've also instantiated 2 parts of our system. So if you look down here, we have a computer part property is now instantiated, as well as the engine part property. So if I were to run that simulation from this engine block, you would only see the engine part of this running. And since there's nothing really associated with that, you don't see anything below that in the simulation variables pane. However, if you want to pull in all the parts of your system, you need to tease that one level higher in order to do that. So I will use that system block, and then we'll instantiate and have object IDs now for those parts of our system. Notice that reference property still did not start up, and that's fine because we're not too concerned with the reference property at the moment, and I'll actually delete that for simplicity's sake. So let's say this is our system. What's good to know about if you were to have multiple behaviors associated with these parts of your system is there's something that is called a classifier behavior. And this is a very important term that is called classifier behavior. So if we look into the specification of this system block now, because we created that activity in the context of that system block, we now have an own behavior that is called system, because that is that activity that we created, but then is also the same activity as the classifier behavior. So the classifier behavior is the main behavior. It is the behavior that will begin when this part property is instantiated, and or when this block is instantiated. So when we run this, that's why that starts up automatically, and you'll see that over here. So system, which is the name of that activity that we did not give a very good name to, has now started. and it's instantiated, and it's because it's a classifier behavior. If you were to go into the specification and unspecify that, which you can do and can be very useful to do in certain situations, we can simply change that to unspecified. Notice it's still a known behavior, but it's not the classifier behavior. So when we start this system block again, what you'll see is no behavior begins. That activity actually does not start. So we can drag in a diagram, the diagram element of that activity, view that, and you'll notice that nothing is actually happening. So again, how did we just do that? How did we get that diagram in view on this block definition diagram? Well, if you notice, we have an activity. Let's just rename this activity. We'll call it get RPM data, or we'll call it send RPM data. So that's the activity behavior element, but then there's also a diagram associated with that. So if you were to simply grab the diagram element, you can use the little eye icon and display that, and that will also come to life during the simulation. So let's go back to the idea of classifier behavior again. If we go back to this system block now, we can reselect that classifier behavior and say we'd like to use send RPM data as the classifier behavior. And now when we start this simulation, we will see that start up again automatically when we push the play button. So classifier behavior is a very important subject, and you can use that to your advantage and disadvantage in a lot of different scenarios. So let's say we want to do some things with this engine and with this computer. Maybe we actually want to send something from the engine to the computer. Let's say we actually want to move that behavior down to the engine. Well, we can do that. We can simply grab this activity in the containment tree, drag it up to the engine, and maybe we will also take that engine RPM and drag it down to the engine block. So when we did that, because that was the first behavior of the engine, that should now be the classifier behavior of the engine, and it is. And because we will run this simulation from the context of the system block, it will not only start up its classifier behavior if it has one, but it will also start up the classifier behaviors of all of the part properties below that. So if this had more parts and they had classifier behaviors, all of those behaviors would begin when you run that simulation from that highest level context. So let's go ahead and rerun this simulation now. And notice we have send RPM data is now running, but it's being actually run from the engine part of that system. And we see that here. It says send RPM data. Part of the engine is actually performing that function or that behavior. And now let's say we actually want to send that data to the computer. Well, you can do that by creating another activity in the context of this block. So we'll create another activity diagram. And then let's say we want to capture that. So to capture data, you'll use an accept event action. And then we can, before we drag the signal onto this, a good thing to know is setting a default property or changing a default property of the accept event action to is unmarshal true. And what that really means is it'll parse out any properties of that signal for you when you drag the signal onto that. So that's good to set beforehand before you actually drag the signal onto an accept event action. So this will be what receives the data. And then what we will do is simply update a property in the context of the computer. So let's create a new value property of the computer, and we will call this RPM data. And then we will type that as a real number as well. So in order to capture that data within this context, we can use another opaque action. And we can say RPM data equals input value. and input value will be whatever's being input into this opaque action, and just so happens to be the default name for pins if you create them as well. So I will leave that just like that, and every time this completes, this accept event action will come back to life again, which is really neat. Now, if you had other accept event actions in here, and then you had those going to other actions as well, if this did not receive a signal, but this did, what will happen is this accept event action will not actually come back to life and be listening again until this accept event action receives its signal as well. So that's something to be aware of. And if you're dealing with scenarios where you have multiple accept event actions, the thing that you would definitely want to do in that case is use a fork node and then actually create some loops below these, right? So we would do a loop here, and then I think I used a join node by accident. So let's say we added a fork node. What you'll always want to do is use that merge node if you're creating a loop. And in this case, we would need to create a loop if you had those multiple accept event actions in that same activity. So going here to here, and then you can go directly back up to that merge node. And that is what you would need to do, as I mentioned, if you have multiple accept event actions and you aren't expecting them to be accepted at the same time. So let's go ahead and we can watch both of these run at the same time by looking at that computer behavior now and pulling in the diagram. So something good to really keep watch of is your levels of abstraction in your model, or the different tiers that you're actually running behaviors in when you run a simulation. So notice in this simulation, this system block will not actually have a behavior, and it's because due to the fact that we have parts of our system, these parts of the system should theoretically be performing all of the emergent behaviors of that block. So this block does not need to do anything theoretically because everything that it is being handled by its parts. And naturally what makes it this abstract thing above that, it's called the system. So if the engine had more parts, then the engine block, or the engine would not need to be running any behaviors at that point as well, because all of its behaviors would be the emergent behaviors of the parts. So that's just something to keep in mind as you decompose your system and you're running simulations, is that typically you don't want to have behaviors running at multiple levels of abstraction in your model. So I will run the system block to run this simulation. And notice down here we can see our runtime values. So let's change the engine RPM data to 25. And then as we see, we are not capturing that data. And it's because though it's sending this signal, it's sending it down here and it says it's not been consumed and removed from the pool. So when a signal is sent in Cameo, it's actually sent to a pool. It's somewhat of a holding area until it sees whether or not that can be accepted. So what we need to do is actually create a line of communication in our model between the engine and the computer. And the way we do that is actually one level above that by creating an internal block diagram. So we'll go to create diagram, use an internal block diagram, and then we'll bring in both of these parts of our system, and then we will create a pathway of communication between these parts of our system. And to do that, we use proxy ports. You can also use full ports, but it is not necessary. I'd recommend simply using a proxy port for this and then use a connector. So that connector indicates that there's some communication that is allowable between these parts of your system. And then we could name this port if we wanted to. We could call this engine interface. I know some people like to use the, different naming conventions for these. Some people like I in front of that. But regardless of your naming conventions, it's good to have name for those. That way you can designate those. So in order to designate how we get this signal from the engine to the computer, we can go into the diagram and we can right click on the send signal action. And I recommend in this case narrowing your properties down to the standard view. And then notice we have this option for on port. So this send signal action will send this signal via this port if we designate it. And because we now have a port from the engine, we can designate that it will leave that port and it will end up wherever it has a connector path to. And in this case, that will be the computer. So we now notice we designated on port and now it says via engine IF, and that's the name of our proxy port. So now when we run the simulation from the system block again, before we do that, we can actually pull in the IBD the same way you can the activity diagrams, and you can watch these signals traverse those connectors. I'll slow it down a little bit. And then notice you see that now traversing the connector from one part of your system to another part of your system. So we have all of that happening. Let's change the value of the engine and watch how that data would actually be sent. Nice, the RPM data is the name of the signal, and then it's outputting that value. And then at that point, you could send that to really any other type of algorithm that you wanted to. If you were creating some type of a model that would react to that engine RPM data, or maybe you're simply saving that data. So that is some very basics of simulations with activity diagrams. The really neat thing about doing simulations is that you can really bring your model to life, and you can simulate almost every one of the 9 SysML diagram types at the same time if you wanted to, and they can all work together in different ways to do different types of simulations. So a lot of people like using state machines. Those can be fun to do. But keep in mind, states are really there to encapsulate behaviors at specific times and inhibit those behaviors at other times. So that's what state machines are good for, is actually inhibiting certain behaviors from happening unless that part of your system is in a specific state. And a lot of times those states end up having a name, and then they simply call these other behaviors. So a lot of times you'll end up right back at where you started with activity diagrams, but state machines can be really useful for that as well. So then the other type of behavior you can simulate are the interaction behaviors, which are what you see on sequence diagrams. And those are very neat as well. I won't jump into that because this is basics at the moment, but I do have some videos on the topic of interactions and sequence diagrams that you might want to look at as well. Salius has some on his MBSE execution channel. So I definitely recommend looking into that. As far as basics of using parametrics, Salius has some videos on that as well. And I have a video on some parametric basics. So I would recommend checking those out. But for now, I think this should get you guys started in the right direction when you're running simulations. If you have any questions on any of this, please feel free to reach out. Thanks.